let's talk about graphs as a data structure. Graphs are a bunch of nodes that are going to be connected with edges. And we are going to have bidirectional graphs where you can go back and forth, that the edge is bidirectional, or directed graphs where we can only go one direction from a node to a given node. Let's start with bidirectional graphs. And within this graph structure, we are going to explore a couple of different algorithms. So our first graph is made up of some nodes that are integers, 0, 1, 2, 3, and they're connected in a circle, 0 to 1, 1 to 2, 2 to 3, 3 to 0. So we have our set of edges that show the connections. And we want to see if we can get, given the set of edges, from the starting node 0 to an ending node 7. In this graph, there is no 7, so we are going to fail, but this is a good demonstration of the algorithm. So let's go to isReachable function. So isReachable function, we want to create an adjacency list, and we are going to assume that our node values are in the range 0 to 99. And so we are going to have a vector, and for each index, 0 to 99, we are going to have a vector of integers that show what that index is connected to. An alternative would be to use some kind of an unordered map that goes from an integer to a vector of integers. If we had more than 100, or if they weren't integers, we would use an unordered map. But for now, let's stick to the vector data structure. So for the vector data structure, we are going to go through all of our edges, and we'll make sure that we are adding our edges so that we create our adjacency data structure. And so, for example, we have our first is 2, second is 3, so 2 is connected to 3. So at index 2 of the graph, we are going to put 3 into the vector of all the nodes that 2 is connected to. And similarly, for graph at index 3, we are going to put it into the vector of all the things that 3 is connected to. Once we have done our connections, we are going to test out two different functions, breadth first search and depth first search. So our breadth first search function uses a queue data structure, and we can think about breadth first search as throwing a rock into a pond when you see the ripples, the set of circles getting bigger and bigger and bigger. Breadth first search works in a similar way. It's going to check if we can find the node that's at a distance of 1, and then at a distance of 2, and then at a distance of 3, and at a distance of 4, and so on. So the queue is going to hold all of our neighboring vertices, all of our neighboring nodes that are just a set distance away. And because graphs can have circularities, we are also going to keep an unordered set of visited vertices, so we don't visit them again. And we are going to put into our queue our starting node, and we can think of it as the kind of the middle of our circle. And we put our starting node saying, hey, that has been visited. We no longer have to visit it again. So we'll process our queue. And so we start with node 0. If this is the node that we want, if this is our target, then we can just return true. If not, we are going to look through all of our neighbors, all of the ones that 0 is connected to, And in this case, because we have a circular structure, 0 is connected to 1 and 0 is connected to 3. So, for example, for neighbor 1, we'll see if it has been visited. If it hasn't been visited, we'll say, hey, we are going to be visiting that neighbor and push that into our queue structure. Similarly, for our node 3, we are going to check if it's been visited. It hasn't, so we'll put it into our queue and push it into our queue. So now we have our queue. We have just put 1 and then 3 in there. So we'll continue with 1. So we are looking at node 1. That's not the node we want. So now we'll look at all of the nodes that 1 is going to be connected to. 1 is connected to 0 and 2. And so first, we look at our neighbor 0, and it turns out neighbor 0 is visited, so we don't put it back in the queue. And then our next neighbor is going to be 2, and 2 has not been visited, so we put it into our queue. So it's gone to the back of the queue. Next, we are going to look at our node 3. 3, just like 1, is 1 distance away from 0. And since we haven't gotten to our target, which is 7, we skipped it. And then we look at all of the neighbors of our neighbor. Sorry, all of the neighbors of our node 3. 3 has the neighbors 0 and 2. In the case of 2, it has been visited. In the case of 0, it has been visited, so nothing goes into the queue. Next, we look at our node 3. That's not the node we are looking for. We look at our neighbors, and 1 has been visited. 3 has been visited, so nothing to put. And now our queue is empty. As a result, we are going to return false from breadth first search. Depth first search works in a similar way, but instead of using a queue data structure, it uses a stack type data structure. So what that means is that we are going to go to one of the neighbors and then keep going to the next neighbor and the next neighbor, keep following that until we can't. And if we need to, then we'll go back and look at the other neighbors. So let's look through that one. So we have a stack. Once again, we need to keep track of visited vertices so we don't have loops. We start from 0. Our node is currently 0. That's not the target we are looking for. We look at our neighbors of 0. Neighbors of 0 are going to be 1 and 3. So 1 hasn't been visited, so we put it into our stack. Next, we look at 3. 3 hasn't been visited, so we put it into our stack as well. Now we have 1 in the stack and then 3 in the stack. So we'll take the top node out of it. So from the 3, we'll look at 3's neighbors. 3's neighbors are going to be 2, which is going to get put into the stack, as well as 0, which doesn't get put into the stack. So we have gone from 0 to 3, and now we are going to, and then we put 2 into the stack, so 2 comes out of the stack, and we look at 2's neighbors. And we continue until we run out of everything in the stack, and once we have exhausted it, we end up returning false. So in this case, We did a BFS where we looked at the nodes at the distance 1, distance 2, distance 3, and then we looked at DFS where we started from a node and kept following the set of nodes. And then if we get stuck, we would go back and look at the other nodes that were in the stack. We can also do DFS recursively. So to do DFS recursively, we are going to press the graph, the starting node 0, our target node 7, and this time, because it's a recursive function, we are going to define our unordered set of visited nodes outside of the function and kind of pass it in. So DFS recursive is going to check if we are at the target. If we are not at the target, say that we have visited that node. And for all of the neighbors, call DFS recursive again. And if the DFS recursive returns true, then we'll return true. If not, at the very end, we'll end up returning false. So in this example, we looked at BFS. BFS didn't find the target 7. DFS didn't find the target 7. DFS recursive didn't find the 7. So none of them were able to find the 7. And we got the same result on all of the graph algorithms as expected. So in terms of our reachability, well, from 0, we really can't reach 7. So let's also look at something that is reachable, in this case, 0 to 3, and kind of go through the algorithm. So once again, we have putting the edges into an adjacency list. Then we are going to go to BFS. We are starting from 0 and we are searching for 3. We initialized, we are starting from 0. 0 is not our target. We look at all of our neighbors. Our neighbors from 0 are going to be 1 and 3. So those are going to get pushed into our queue. And then we continue processing the queue. And now we took out 1. And 1 is not our target. We put 1's neighbors into our queue. And next, we are going to take 3 out. And 3 is our target. So we end up returning true from BFS. In terms of DFS, once again, the same kind of algorithm, but instead of a queue structure, we are using a stack structure. We are starting from 0, and 0 is not our target. We look at our neighbors. Our neighbors are going to be 1 and 3. So we push them onto the stack. So next, we look at the node 3 from the stack, and hey, we found it as our target, and we can return true. In terms of DFS recursive, we are going to have the same process, but in a recursive version. So once again, all of our graph algorithms return the same result. We are able to get from 0 to 3. When we are using breadth first search or depth first search, our edges don't have any weights to them. They might have directionality, but they don't have any weights. Later, we are going to see edges that have a certain length, such as a road as part of it. So we have reached 3. Let's look at one more graph to get a better understanding of breadth first search and depth first search. So in this case, we have a tree-like structure. We have 0 at the top, 1 and 2 as the children. 1 has 3 and 4, and then 2 has 5 and 6. Then 3 has 7, and then 4 has 8 as its uh, as its child. So we provide these as edges. Once again, we look at if it's reachable. We create our adjacency list. Let's put a breakpoint here and just continue. And then let's start from BFS. We are going to use a queue structure. So we are going to start from 0 is our node. 0 we said had 1 and 2. So we are trying to get to a target of 7. So in this case, our neighbors are 1 and 2. So we are going to put our neighbor 1 into the queue. And next, we are putting our neighbor 2 into the queue. And now we go back and process the queue again. So we are now looking at our node 1 that's in the queue. And node 1 has neighbors 0. So it can go up to the parents since it's directional. But since it's been visited, we don't want to go to 0. From node 1, we can also go to 3. So we put that one into our queue and 4 into our queue. Next, we are going to look at the node 2. So 0 had 1 and 2 as its children. We looked at all of the children of 1 and we put them in the queue. Now we are going to look at 2 and put all of its children in the queue as well. So we go through two's neighbors. 0 is a neighbor we don't put, but also has 5 we put into the queue and 6 into the queue. Our queue is not empty, so now we are looking at node 3. Node 3 has node 1, which is the parent, as a neighbor. We don't put it there. It also has 7 as one of its neighbor. Although we are finding 7, we don't immediately return. We are going to put it into the queue and wait for the queue to do its thing. So we put 7 into the queue. And now we are going to look at 4's neighbors. We put them in the queue. Next, we are looking at 5's neighbors. We put them into the queue. And then we are looking at 6 neighbors. We put them into the queue. And finally, we are looking at 7 and say, hey, 7 is our target, so we can return true as part of it. So we covered it using breadth first search. So if it was a tree-like structure, we can think of it going level by level by level, extending each level at a time. Oh, I skipped the, let's see if I can go back. Let's see, we want to go through graph 1. We don't care about the graph 1 right now. I want to go to graph 2's reachability for 7. So let's go there. And then I want to go to the DFS for that one. So let's quickly go through the adjacency. Okay. So let's look at depth first search going from 0 to 7. So we are putting a stack-like structure. We are starting from 0. We put it onto the stack. Then we pop it from the stack. It's not what we are looking for. So we look at its neighbors. 0 has the neighbors 1 and 2. So we put 1 into the queue and then 2 into the queue. Now we are going to look at 2 that's on the stack. Look at its neighbors. 0, which is the parent of 2, or is a neighbor. We don't put it onto the queue. 2 has additionally 5 and 6 as part of it. So they go onto the stack. Now, then we look at 6. Next, we look at 5. And then we are going to look at 1, which is going to have neighbors 3 and 4. Then we are going to look at 4 and 4 has neighbor 8. So finally, we look at 8. 8 doesn't have it. And we are still looking. And finally, we are pushing 7 as a neighbor. And we get 7 out. And we have done it. So maybe it will be helpful to kind of have a little graph of what we have been looking at. So let's have a look. So we started with 0, and 0 had 1 and 2. 1 had 3 and 4. 2 had 5 and 6. And then 3 had 7, and 4 had 8. So based on that, we started from 0. Let me see if I can pick another color. So let's pick another color. So we started from 0. We put 1 on the stack and then 2 on the stack. Since 2 was the top of the stack, we went this way. From 2, we looked at its neighbors. 5 on the we put 5 on the stack and then 6 on the stack, and then we visited 6. 6. Well, its only neighbor is 2, which has already been visited, so we didn't visit that. So we came back to 2 and visited its neighbor 5. From 5, it had no other neighbors to add, so we went back to 2, then we went back to 0. So now we have processed all of 0's neighbors that go from 2. Now we went to 1. We looked at its neighbors in the depth first search, 3 and 4. 3 went on the stack, and then 4 went on the stack. So we explored 4, then we explored 8. Then having nothing else at those levels, we went back, and then we explored 3, and finally we explored 7 to find it. So depth first search chooses a direction and keeps going as much as possible. And when it hits a dead end, it goes back up, and then it goes down as part of it. Let's see if we can clear this annotation so we don't have to suffer from it. Clearing all drawings. Let's continue. And if we wanted to do DFS recursive, going from 0 to 7, we'll have a similar structure. But now for each neighbor, we are kind of trying it out first. So this time we are trying out if we can get to 7 from 1. So if we go into there, 1 is not our node, so we put it into our visited. Then we look 0 is visited. The next one that we are going to look at is from 3. So we are going 0, 1, 3, and then it's going to be 7. So we go here. So our 1 has already been visited. Now it's going to be looking at 7. We go into recursive. Our node 7 is equal to our target, so we return true, which returns true from the recursive loop, which also returns true, which also returns true. So our recursive DFS ends up returning true for all of them. So in this case, we can use the same algorithm to check using BFS and DFS if something is reachable. So breadth first search and depth first search are both good algorithms. One thing to remember is breadth first search is going to find the shortest path if we are keeping track of the path, because it's going to explore everything at a distance of 1, then at a distance of 2, then at a distance of 3. So it's going to find it at the shortest distance possible. Whereas DFS might take a very long way to get to its destination. And that's breadth first search and depth first search algorithms.